So today let's have a look at the second half of C1L1, equations of motion. So imagine you are driving a car along a road at a constant speed, and suddenly you see a deer crossing the road ahead of you, as shown here in this figure. And you apply your brakes, slowing the car down. If you slow down at a constant rate, how far will you travel before you stop? Will you hit the animal? To solve this kind of problem, you can use motion graphs. Using these graphs, you can calculate distance you will travel while applying the brakes, which is the braking distance. You can also determine your braking time. The braking time is how long it takes to stop while applying the brakes. There's another way to solve the problem. Using motion equations. Motion equations relate different variables such as velocity, acceleration, and displacement. In most cases, it is easier and faster to solve problems using motion equations than by drawing motion graphs. For motion with constant acceleration, motion equations can relate 5 variables: the object's initial velocity, its final velocity, its acceleration, displacement, and time interval. Okay, I'll repeat. 5 variables can be related using motion equations. They are the object's initial velocity, final velocity, acceleration, displacement, and the time interval. Okay, so first of all, let's have a look at one-dimensional motion with constant acceleration. The defining equation for average acceleration is given below. The average acceleration, A, average, equals the difference between the final velocity, Vf, minus the initial velocity, Vi, over delta t. So note that all of the variables except the time, delta t, are vectors. So in one-dimensional case, if your variable is a vector, that means they could be either positive or negative, right? There are only 2 directions in one-dimensional motion. So first of all, when solving a problem, you should specify your positive direction, and then any vector could be positive or negative. Positive vector means the direction is the same with your specified positive direction. Otherwise, if your variable is negative, that means the direction is the opposite to the positive direction you defined. So in this section, and for all our equations of motion, the acceleration is constant. So we will use the symbol A instead of A average, okay? So again, when the acceleration is constant, we'll use the symbol A. So here, as you can see on the right, figure 2 shows a velocity time graph for an object with constant acceleration. The object starts with initial velocity Vi, accelerates for a time delta t with acceleration A, and ends with final velocity Vf. Then, from this graph, we know the displacement is equal to the area under the line, right? The shape under the line is a trapezoid, and its area can be given by delta D equals 1/2 of the sum of Vf plus Vi, then times delta T, right? So that is the displacement given Vf, Vi, and delta T. Also notice that the above equation does not use the variable A. This means we can combine it with the defining equation for average acceleration to derive other useful equations. There are 5 variables: delta t, displacement, initial velocity, final velocity, and acceleration. And we can derive equations and link any 4 of them. So for example, to eliminate VF, we can combine our equations. We can rearrange the defining equation for average velocity to get VF, right? Because we have this relationship here. Acceleration A equals the difference between the final velocity and the initial velocity over delta t. This is our average velocity, average acceleration, right? On the other hand, we also have from this equation, we can have final velocity VF equals initial velocity VI plus average acceleration A times delta t, right? Then we can substituting the above equation for VF into the equation for displacement. And this gives us the following equation. Delta t, as you can see here on the bottom left, this formula, delta t equals 1/2 of the sum of VF and VI times delta t, right? Then substitute VF, use A times delta t, then that gives us delta d equals 1/2 of the sum of VI plus A times delta t, then plus another VI, then times delta t. And simplify this equation, you can get displacement delta t equals initial velocity VI times delta t plus 1/2 of A times delta t. So this is a displacement formula for a constant constant acceleration in one-dimensional motion. Then we can use similar substitutions to derive 2 more equations that eliminate the initial velocity VI and time interval delta t. And then the equations of motion for constant acceleration rate can be shown here on this graph. So these are the common formulas we can use in one-dimensional motion with constant acceleration, okay? Well, these are the 5 key equations for uniformly accelerated motion, which means motion with constant acceleration. Also note that these formulas, so far we have only talked about one-dimensional case, okay? Okay, I'll give you some time to have a look at these equations. So you should be able to derive them from the definition of average acceleration and the motion graphs, okay? And then I'll show you some concrete examples to illustrate how we can use these equations to solve problems. Okay, I'll give you 5 minutes to have a look at them. Also note that in these equations, variables are all vectors, right? So when you use this equation, make sure that you include the positive or negative symbol of your variable, okay? So first of all, you should define a positive direction. And if your variable is with the same direction with a defined positive direction, that means your variable should be positive. Otherwise, that variable should be negative, right? So please keep the positive or negative symbol of your variable when you use these equations. Okay, any questions? Then let's have a look at a sample problem to have a look at how we can use these formulas to solve real world problems. Okay, so first of all, let's consider this problem, solving for time and final velocity. Given two cars are at rest on a straight road, car A starts 120 meters ahead of car B, and both begin moving in the same direction. At the same time, car A moves at a constant velocity of 7.0 meters per second, and the direction is forward. car B moves at a constant acceleration of 2.0 meters per square second. The direction of the acceleration is also forward. Can you calculate how long it will take for car B to catch up with car A? And calculate the velocities of the two cars when they meet. Okay, I'll give you 5 minutes to have a look at this question by yourself, and then we'll discuss the solution together. All right, have you finished? Let's have a look at the solution. Okay, so let's analyze this problem first. The information given is we have two sets of variables, right? One for each car. So first of all, we'll label them with subscripts A and B. So all the variables for car A are with subscripts A, and for car B with subscripts B. So we know the initial velocity of VA and VB and acceleration of A and B, right? So VAI is 7.0 meters per second. Direction is move forward. Acceleration A is 0 because car A moves at constant speed, a constant velocity. So acceleration is 0. Initial velocity of car B is VBI equals 0. And acceleration of car B is 2 meters per second, square second. Direction is also forward. So the variable required is the time interval delta t and the final velocity of car A and car B respectively. So we can use this formula, delta t equals VI times delta t plus 1/2 times acceleration A times delta t squared. So express the displacement of each car using forward as positive. So here we define the positive direction is forward, okay? And then we can relate the two displacements. When the two cars meet, their displacement should be the same, right? Okay, so the displacement of car A from its starting position is given by delta D equals VI times T plus 1/2 of A times delta T squared. And then just put all the values in. Note that initial velocity is 7, right? Because initial velocity is forward, so you should use positive 7. Then acceleration is 0, so that cancels the second part. Therefore, we know the displacement for car A, delta dA, is 7 delta t, right? The displacement of car B from its starting position is given by also this formula, and then put all the values in. Then we can find displacement of car B is delta t squared, and direction is forward. Then we want to solve for the time at which car B has caught up with car A, right? So this happens when delta D B equals delta A plus 120. Delta dA plus 120. Because for car B to catch up, it has to cover the initial 120 meters as well as displacement of car A, right? So using our expressions for delta dA and delta dB, we can get the following quadratic equation. delta dB equals delta dA plus 120. And this is equivalent to delta t squared plus 7 delta t plus 120. Also, we are omitting the units here to keep the equation uncluttered. Rearranging gives the equation below. Delta t squared minus 7 delta t minus 120 equals 0. So from here, you can either solve this equation using factorization or using the quadratic formula, right? Note that there are two solutions here. One of them is delta t equals 15. Unit is seconds. Second solution is delta t equals -8. So note here, delta t could not be negative number in the real world problem, right? So we want the positive time value only. Therefore, we know delta t is 15 seconds. Since car A is not accelerating, we can find velocity of car A at the end of this process, which is VAF equals VAI, which is 7 meters per second, right? And for car B, we know the final acceleration VBF equals VBI plus AB times delta t. And then put all the values in. That gives us final velocity of car B is 3 times 10 to the power of 1, which is actually 30 minutes per second. Direction is move forward. So we can make the final statement here. Car B catches up with car A after 15 seconds. When they meet, the velocity of car A is 7 meters per second. Direction is forward. And the velocity of car B is 30 minutes per second. 30 meters per second, and direction is forward. Any questions? Okay, so note here, this is just a solution using one type of notations. If you prefer use your own notations, that'll be fine. But please remember, in the at the very beginning, you should specify your positive direction. Okay. Okay, then let's have a look at another problem here. This time we have a motorcyclist drives along a straight road with a velocity of 30 meters per second. Direction is forward. The driver applies brakes and slows down at 5 meters per square second. And the direction of the acceleration is backward. Then there are two questions. First, calculate the braking time. B, determine the braking distance. Okay, again, I'll give you 5 minutes to try to solve this question by yourself first. Okay, then we'll have a look at the solution together. have a look at the solution together. So first of all, let's analyze this question. So we can treat this process as a motion in one-dimensional space, right? And it says the driver applies the brakes and slows down at 5 meters per square second. So we can assume this is a uniformly accelerated motion in one-dimensional space, right? So let's first state this. This process can be considered as uniformly accelerated motion in 1D space. Okay, so we can use a model in one-dimensional space of a uniformly accelerated motion to solve this problem. Remember, first of all, we should specify the positive direction, right? Because in one-dimensional space, there are two directions. So we let the direction of the initial velocity of the motorcycle motorcyclist be the positive direction. Okay, so after you specify the positive direction, we know the initial speed initial velocity is vi. So here you could use either this symbol or just vi. So for simplicity reasons, I'm gonna use vi here, okay? And use the symbols, a positive or negative symbol, to specify the directions. Okay, so we know the initial velocity is vi, which is 30 meters per second, right? Because it had the same direction with positive direction. And when the driver stops, the final velocity is Vf. Again, I'm going to use a symbol here. For simplicity reasons, I don't put an arrow on top of it, which is 0 meters per second, right? And for the first question, we want to calculate the braking time. So note that we have the following relationship. Final velocity equals initial velocity plus a times time interval t, right? Also, because we don't have t in the question, so you need to, before you use any variables that is not in this question, you have to specify meaning of that variable, okay? So we can say let t denote the braking time, which means the time interval taken for the driver to stop, okay? Then we have the following relationship. Vf equals vi, initial speed plus at, right? That's what the model tells us. Final velocity equals initial velocity plus at. Also note here, all these variables should be vectors, okay? They have the symbol, either positive or negative, in front of each quantity. So that gives us, we know the final velocity is 30. Initial velocity is 0, plus a is unknown. Oh, sorry, I didn't specify. I haven't specified A, right? Because A is not in the question yet. So let's say where A is the average acceleration in this process. And we all know that A equals, if the positive direction is the same with initial velocity, we know the acceleration is backward. That means A equals -5 meters per square second, right? So we have VF is 0 equals VI, initial velocity is 30 plus -5 times t. Make sure each of the variable here, when you use them into your, when you substitute the numbers into your equation, make sure they are in SI unit. Okay, so the SI unit for velocity is meters per second. SI unit for acceleration is meters per square second. Then the solution of your t should be in SI unit as well, which is second, right? This gives us t should equal 6. SI unit is seconds, right? Therefore, it will take 6 seconds for the motorcyclist to stop. So the conclusion is the braking time is 6 seconds. Okay, that's for question A. Then let's consider question B. Determine the braking distance. Okay, there are a number of ways to calculate braking distance. If you don't want to use the time interval here, you can use this formula. Remember, VT squared minus V. Oh, sorry, you should use VF here. There is a formula saying VF squared minus VI squared equals 2AS, right? You can use this formula to solve this question. So again, we can use S, denote, or you could use S or D, doesn't matter. So let's, for example, let's say let D denote the displacement. In this process. Then we have the following relationship. VF, oh, sorry. VF okay, let's write it here. VF squared minus VI squared equals 2AS. Also, please be careful with all the variables here. All variables are vectors in one-dimensional space. That means you should keep the sign, whether positive or negative, into that equation, okay? So that gives us final velocity is 0 minus initial velocity is 30 equals 2 times A, which is -5 times distance. Oh, sorry, no, not S, but times D, right? That gives us D equals 900 over -10. Therefore, we have 90. Again, SI unit for displacement is meters. So the displacement is 90 meters when the motorcyclist stop the motorcycle. Any questions? Okay, of course, you can also use this formula to solve displacement. So displacement equals initial speed vi times t plus 1/2 of acceleration times t, okay? Also, rigorously speaking, you should use a notation for vectors because all of these variables should be vectors. But specifically in one-dimensional case, it's okay to use these letters as long as you know these are all vectors, okay? So you could also put arrows on top of each vectors. So you could use either this one or this formula to solve this question. You understand? Okay. All right, if you don't have any questions, let's have a look at another concept, which is about freely falling objects. So when you let go of a ball, it will fall down because Earth's gravity pulls it down, right? When you throw a ball upward, it will move upward for a time, stop, change direction, and then move downward. In both cases, a ball is moving under the influence of gravity. An object that is only moving under the influence of a gravity is said to be in free fall. The ball is in free fall when you drop it. The ball is in free fall when you throw it upward. Gravity moves objects downward with a constant acceleration of approximately 9.8 meters per square second. The important value is called the acceleration due to gravity, usually denoted by lowercase g. On Earth, other factors affect moving objects, such as air resistance. You will read more about air resistance in the next chapter. We'll study that in the next chapter, okay? Okay, then let's consider another example here, which is about using the equations of motion for accelerated motion due to gravity. So here, a ball is thrown from a height of 52 meters from the top of a building with a velocity of 24 meters per second, straight up. So there are two questions. First, determine the velocity of the ball at ground level. Second, how long does it take for the ball to reach the ground? Okay, I'll give you 5 minutes to have a look at this problem by yourself, and then we'll have a look at the solution together. Okay, have you finished? Let's have a look at the solution here. Okay, so in this question, we are given the initial velocity of the ball, which is vi equals 24 meters per second. Direction is up, right? So note here, if you do not specify the positive direction at the very beginning, you should keep the direction of each of the vectors here, okay? Otherwise, if you specify the positive direction at the very beginning, then you should say the velocity is just 24 meters per second. The positive symbol in front of the quantity here means the direction of a variable should be the same with your specified positive direction. So in this case, we don't specify the direction at the very beginning. So this is just another notation, okay? So we keep the direction of each of the variables, each of the vectors in the square parentheses after the magnitude of that variable. Okay, so basically we are given initial velocity vi equals 24 meters per second, direction is up, and the acceleration due to gravity g is 9.8 meters per second, direction is down. Also, we know the displacement of the ball is 52 meters, direction is down. And we require the velocity when the ball hits the ground, which is the final velocity denoted by Vf. So we can use this formula, Vf squared equals Vi squared plus 2a delta d to calculate the final velocity. We can use up as positive and down as negative. Okay, so according to this formula, Vf squared equals 24 meters per square 24 meters per second square plus 2 times negative 9.8 meters per square second times negative 50 meters. So note here, if you use the positive direction as use up as a positive direction, displacement is also negative, right? Therefore, we have two solutions, either Vf equals positive or negative 39.9 meters per second. Since the ball is moving down, we should keep the negative value. Therefore, we know the velocity of the ball at the ground level is approximately negative 40 meters per second. This is one of the notation, right? The other type of notation is you could also use 40 meters per second and then followed by a square parenthesis specifying the direction, which is down. And in question B, we are given initial velocity 24 meters per second. Final velocity is negative 39.9 meters per second. And acceleration due to gravity is negative 9.8 meters per square second. And this time we require the time interval delta t. Note that we have the following relationship, right? Acceleration A equals Vf minus Vi over delta t. So delta t equals Vf minus Vi over acceleration A. Therefore, put all the values in because we know Vf, Vi, and A. Put all the values in, we have delta t is approximately 6.5 seconds. Therefore, we can make the final statement. It will take approximately 6.5 seconds for the ball to reach the ground. Okay, have a look at this question here. Do you have any questions? Okay, if not, that concludes our second part of C1L1. And also, please remember to complete today's homework and submit that to Google Classroom. Okay, I'll see you next time.